So now we're going to state the inverse function theorem. Of course, proving it is it takes a little more effort than and some more tools than we have at our disposal. But we can apply it. So suppose we have this function f(xy) is equal to x minus 1 squared plus y minus 1 squared. And in the second coordinate, or the second component, I have x squared plus 2xy plus, let me see here, let's say y squared plus 2x, that's an x, I swear, plus y. That's our guy. Well, at 0, 0, we have that f of 0, 0 is equal to 2, 0. That's easy to compute. And we can compute the Jacobian at this point. So df1 dx at 0, 0. df2, or still f1 dy of 0, 0. df2 dx at 0, 0. And df2 dy at 0, 0. Well, computing that is simple. We've got our polynomials and we just plug them in. We get minus 2, 2, 1. And this is equal to df at 0, 0. This is my Jacobian. Well, since, and it's pretty easy to compute the determinant of that, which is not 0, and since df 0, 0 is invertible, we may locally solve for to 0 plus negative 2 to 1 x minus 0, right? So these are the points. Y minus 0 is equal to b1 and b2. And really, this should be approximately, right? So this is my linear approximation to the function at that point, and I want to invert that linear approximation to compute what does my x value and my y value have to be to get b1 and b2, right? And we can do this for any b1 and b2, of course, but it only makes sense if b1 and b2 are really close, say, to 2, 0, right? And this is a good approximation if b1, b2 is approximately 2, 0, right? So this is the good local picture, and in particular df 0, 0 is onto and 1 to 1 at 0, 0. So we know that f is locally onto and 1 to 1 at 0, 0. That's by our theorem that we stated last time, right? And so let's get to the theorem. So theorem, this is the inverse function theorem. So let f from Rn into Rn be C1 with f x star is equal to y star if df at x star is non-singular, then there are open balls or open regions around x star, y star, and we'll call them x, y, such that f is 1 to 1 and onto between these regions. Right, so I'm restricting f, and I'm saying f is only now going to be defined on x, right? And it turns out that the inverse function theorem tells me that y is actually the entire image of x under this map, f. Not only that, it says it's 1-to-1 and onto this thing, right? So that means that we can define an inverse, the inverse map, right? Whenever we have a 1-to-1 and onto, there's the natural inverse map. The inverse map, now it's f inverse from y into x, is also, so when this happens, this guy is also C1, and d of f inverse evaluated at f of x star is equal to d f at x star inverse.